Welcome. Now we shall learn about another processing of the natural gas related to the removal of the gas hydrates from the natural gas. As we learnt earlier that the gas hydrate was also talked about when we were looking into the production of the natural gas from the natural gas hydrate. Now here we see the various ways that how the gas hydrates inhibit the natural gas processing and why they have to be removed. So in this lecture we shall be learning more about the gas hydrates, the need for their removal, how these gas hydrates are formed, the different ways of inhibiting the formation of these hydrates. Then we shall look into some of the estimation methods to find out the formation temperature of the hydrate and the amount of inhibitor required to inhibit their formation. So first let us look into what gas hydrates are. Now gas hydrates are a class of solid ice-like non-stoichiometric compounds. Now in this case we have to see this ice-like. So if I look at this particular picture, we find that this is a gas hydrate and it looks exactly like ice, but the difference is this: we cannot make out the difference between ice and this gas hydrate by our naked eye. We have to do some analysis and we find that this particular piece of apparently solid ice is burning. This burning characteristic tells us this is not water ice, but this is gas hydrate, and this is burning because of the presence of the methane. So these hydrates are different from the salt hydrates which we are more accustomed with in our fundamental of chemistry. So in this, salt hydrates are not these kind of hydrates, because the salt hydrates are stoichiometric compounds, whereas the hydrates are non-stoichiometric compounds. And we have some examples of these salt hydrates like magnesium chloride with 6 water of crystallization, copper sulfate with 5 water of crystallization, similarly magnesium sulfate with 7 water of crystallization, so on and so forth. And these hydrates are formed when water forms a cage structures. And how this cage is formed? This cage is formed by hydrogen bonding among the water molecules, and in this particular cage any guest molecule like this methane, ethane, H2S, CO2, etc. are trapped. There are many gases which can form gas hydrates, and here we see in this particular pictorial representation how we get different type of structures here. Here we find for the methane, for example, has been trapped in a cage of water. In this particular diagram, these black beads are representing the hydrogen molecule, hydrogen atom, whereas these red ones are representing oxygen. And here, depending on the type of this particular cage, we have different types of hydrate structures, and here we have S1 structure, S2 structure and SH structure, structure 1, structure 2 and structure 8, and we find that different gases form different types of these hydrate structures, and these hydrate structures dictate the amount of the gas that can be captured in the particular water cage. Now understand this, all the water cages in the structure may not be completely filled up, some of them may remain partially filled. So, but we have to understand that depending on the type of the guest molecule, the structure will be differing. Now, why these hydrates are not wanted in natural gas system? The reasons are this: first is flow assurance. What is meant by flow assurance? By this we mean that we want to ensure that there is an unrestricted flow of the hydrocarbons from the well to the processing point, and the hydrocarbon flow get hindered by the deposition of the wax and asphaltene solids, the scaling by some inorganic salt deposition, and by the gas hydrates. So all this causes the flow inhibition of the natural gas or the petroleum, so they are unwanted in the system, and gas hydrates are most feared because they can form without any warning, and then they will block the flow quickly, unlike the other depositions, because other depositions take time, but these gas hydrates can form any time all of a sudden. If there are the conditions with respect to the pressure, temperatures and other impurities are favorable. And then if we are using some kind of chemical inhibitors to prevent the gas hydrate formation, even then we find that due to some operational failure of the pumps or the separators, we find that the inhibitors may not be injected properly into the system, so that it may lead to the formation of the gas hydrates in the line. Now, what are the conditions which favor the formation of the gas hydrates? Favoring does not mean that the formation is guaranteed, but the conditions are such that it may lead to the formation of the gas hydrates. Generally, it is at high pressure and low temperatures dictated by the thermodynamics, and we can find this a typical figure which is showing the pressure versus temperature diagram of some hydrocarbon with water, and we find here that this is the zone here within which we find these hydrates are formed. In this zone we find the hydrate and free water is there. In this zone we have hydrate and ice water. That means if we lower the pressure, which if it comes to this particular region, this hydrate will dissociate into the hydrocarbon gas and the ice, and if we are lowering the pressure over here, we will get water and hydrocarbon gas, and in this case we shall get liquid water and hydrocarbon and the water. So, there is a particular zone in which we shall be getting the hydrates. So, these zones have to be avoided whenever we are making any kind of operation. Now, the hydrates are also formed that even if there is in the requisite temperature and pressure, but unless there is sufficient amount of water, the hydrate cannot be formed. So, it needs the presence of water, free water, and then the gas should be at or below the dew point of the water, so that the water can form liquid. It cannot be in the vapor phase, but it should be in the liquid phase. So, it should be the temperature of the gas should be at or below the dew point of the water, and if you are agitating the system, then what happens? By agitation we are able to mix up the gas and the water properly. So, this mixing up will be inducing the gas hydrate formation, and then we have some presence of some seed crystals. If there is some kind of seed crystals, some impurities are there, these seeds are affecting and they will favor the formation of the hydrates, because this hydrate formation is primarily a crystallization process. So, if crystallization is favored by the presence of some kind of seed particles. Now, we find that in case of natural gas, the gas hydrates may form at temperatures well above the freezing point of water, and methane forms the hydrate at the lowest temperature among all the hydrocarbons, because it has the least molecular weight among all the hydrocarbons, and the heavier hydrocarbons cannot form hydrates because they cannot be accommodated in the water cage. So, it is only the lower hydrocarbons which are prone to forming the hydrates, and here in this particular graph we show that how the various types of gases are forming hydrates. Here we have pure methane, and here we have pure ethane, and here we have pure propane, whereas if we mix them up, we find their hydrate formation is happening somewhere in between. And in this particular figure, suppose we take any particular component methane. So, we find this particular line demarcates this hydrate region and this is the non-hydrate region. So, any pressure for a given temperature, any pressure above this pressure will be favorable for hydrate formation. Similarly, for a given pressure, any temperature below this temperature will be favorable for hydrate formation. So, this region above any of these lines is the hydrate formation region, and below the line is the non-hydrate region. Now, here we see that the addition of some of the impurities, higher hydrocarbons, carbon dioxide or H2S, these may raise the hydrate formation temperature. That means the formation may get delayed. The addition of nitrogen has been found to decrease the hydrate formation temperature. So that means if we add hydrogen, then maybe it is good for us to have the delayed hydrate formation, whereas any carbon dioxide H2S, they will raise the formation temperature. Now, there are various ways of predicting the gas hydrate formation condition. First, we find that gas hydrate formation, we want to know the pressure and temperature, or for a given pressure what would be the temperature, or the vice versa. Now, gas hydrate may not form, as I was telling you, that even if we have the thermodynamically favorable condition. Why? Because this hydrate formation is a very complex process which involves crystal formation, and this crystal formation we know that is not an easy task. So, even if we have the right temperature pressure, we may find that the hydrate is not getting formed, but still the operating conditions have to be maintained outside the hydrate formation region to see to it that there is no chance of any hydrate formation. Now, there are various methods proposed in the literature to predict the hydrate formation temperature. I shall be talking about only one of the methods, and this is the method in which we find that this T is the formation temperature for a given pressure P, and this is based on the gas gravity. So, in this particular equation, T is in degree centigrade and P is in bar absolute, and this can also be given graphically. From this particular figure also we can find out that for a given temperature and for a given gas gravity, and you know that gas gravity represents is the equivalent to denoting any particular component. So, even if I know the gas gravity, I can find for a given temperature what would be the formation pressure, or for a given pressure what would be the formation temperature of the gas hydrate. So, any temperature below this temperature or any pressure higher than this pressure will be conducive to the formation of the gas hydrate. Now, there are various ways of inhibiting this hydrate formation. One thing is this: we can operate on the whole system outside the hydrate formation region, but this may always not be possible for the demand of the particular operation. So, we may have to go to those conditions which are conducive to the formation of the hydrate. Now, what we can do, we can thermally heat the line. By heating the line, we are trying to keep the temperature above the formation temperature. But in this case, what happens is this is more convenient for short lines because heaters operate with minimum attention, and there also we need, for heating up, we need some kind of fuel. So, there is energy will be expended for this inhibition of the hydrate formation, and generally for long lines about say more than a mile or so, the gas approaches ambient temperature, and in that case chemical injection is preferred. We can also dehydrate the system, as we learnt in the chapter on the dehydration. That means, if we take out the water and the water level comes down so much so that even if there is the right pressure and right temperature, the gas will not be able to find enough water to form hydrates. So, dehydration is another way of reducing the chances of hydrate formation, and it is generally done for the offshore and if it is economically feasible. And then we have the using some hydrate inhibitors, and these inhibitors are done only if we find that dehydration is not possible, and generally the inhibitors are added at the wellhead or at the booster stations. Now, we have different types of chemical inhibitors. There are three types. First is the anti-agglomerates. How they work? That these chemicals prevent the agglomeration of the hydrate, so that once the agglomeration is prevented, they cannot form the crystal. So, these kind of chemicals act by preventing the agglomerate formation of the hydrates. And then we have the kinetic hydrate inhibitors. By this we mean that they reduce or they retard the rate of formation of the hydrate. That is what kinetic means. And But in this particular type of inhibitor, we find that if the amount of the inhibitor is large, it may lead to the formation of the hydrates. And lastly, we have thermodynamic inhibitors. What they do? They are basically some antifreeze agent, and they lower the temperature of the hydrate formation, so that the hydrate formation gets delayed for a given pressure. And under these thermodynamic inhibitors, we have most common ones are methanol, ethylene glycol and diethylene glycol. We shall be calling them EG and DEG respectively. Now, disadvantages of these chemical inhibitors are that these inhibitors themselves can cause plugging and they are costly, and methanol is lost due to evaporation and glycol is lost not only due to evaporation but also by entrainment by the gas stream, by decomposition or the dissolution in the hydrocarbons. So, these are the disadvantages of the chemical inhibitors. And then we have the unreliability, because these chemical inhibitors have to be injected into the system by some pumping mechanism. If we find that the pump has failed, or we find that wherever we are storing the inhibitors that there is depletion of these inhibitors has happened, then we will find that we may not be able to know it. And this is especially true if these are we are operating at remote site. So, if we are not able to monitor the process properly, we find that this particular operation by use of the chemical inhibitors may not be proving reliable, and these inhibitors may react with other chemical additives, and thereby it will reduce the efficacy of the inhibitor. Now, let us see that how these different thermodynamic inhibitors are working. Like we are talking about the operating temperature. In this case, we find that methanol can operate generally at any temperature. The EG generally works better for minus 9 degrees centigrade or so, because of its lower viscosity and easier separation from the liquid hydrocarbons, whereas DEG is used generally above minus 6 degrees centigrade because it has lower vaporization losses than EG. Now, as far as the depression of the hydrate formation temperature is concerned, methanol is found to be most effective, followed by EG and then DEG. The mixing methods are also important, because how we mix up these particular inhibitors with the natural gas, and unless they get mixed properly, they won't be effective in preventing the hydrate formation. And in this we find that the glycols, that is EG and DEG, are generally spread as fine droplets in the natural gas stream to cause intimate mixing, whereas methanol mixes very easily with the gas as it can itself vaporize. Then we have the freezing effect of glycol, which is not found in case of methanol, that this glycol concentration should be between 60 and 88%, because what happens at this higher side, if you go at for higher concentration and at low temperature, the glycols may become mushy, which inhibits the proper flow. Mushy means they will be kind of a semi-solid, gel-like solid they will form, and that will also prevent the flow and the separation of these glycols from the hydrocarbons. Next, about the regeneration, we find that these diluted glycols are generally regenerated because they are quite costly. On the other hand, methanol may not be regenerated because methanol comes cheap and the cost of regeneration is quite high, and generally we use distillation for separating the methanol from water. So, the cost is high, so and this raw material is also cheap. So, generally regeneration is not done when we are using methanol. Economy wise, we find that glycol proves more economical for large volumes and or for continuous operation, whereas methanol proves more economical for smaller volumes, for infrequent or intermittent operation, and mild hydrate formation problem is there, then we use methanol. Cost wise, we find that methanol injection has low investment cost but high operating cost due to chemical consumption, whereas in case of EG, DEG, the initial cost is more than methanol, but they have lower operating cost because we are able to regenerate these glycols. And action we find that how they are preventing how they are acting, that glycol are preventing the hydrate formation but cannot dissolve the already present hydrates, whereas methanol can dissolve the existing hydrates to some extent. So we have to consider all these factors, and lastly, for long lines, methanol is preferred to glycols. So in choosing these inhibitors, we have to consider all these points. Now if we compare the inhibitor injection with the line heating, we find that line heating cost may depend on the cost of the fuel, and so the cost of investment will be between methanol and glycol. Next we come to the removal of existing hydrate. Now if we have already hydrate present in the system, generally what is done? The pressure is lowered below the hydrate formation pressure at the given temperature, and the pressure must be reduced on both the upstream and downstream side. It is not that we do not reduce the pressure on the downstream side. What if we reduce the pressure if we reduce the downstream pressure without reducing the upstream pressure, what will happen? There will be large pressure difference, and large pressure difference, what will it will lead to? It will lead to this high velocity of the hydrate which break loose from the flow, and this high velocity of the hydrates, what will happen? They can heat the pipeline wall so hard that it may lead to the breakage of the pipeline, or even for the underground pipeline, the pipeline may come out of the earth. So you can see the severity with which these hydrates can act in the pipelines. So whenever we are trying to reduce the pressure, we have to make sure that both on the upstream side and the downstream side, we are reducing the pressure to prevent this kind of occurrence. Next we come to the design of the hydrate inhibition system. In this we shall be just looking to fundamentals without going into detail. The basis is that the hydrate inhibition means that we are transferring the water from the natural gas to the liquid inhibitor. So what happens? That we are in this design, we try to determine the minimum amount of the injection rate of the inhibitors, and that is generally given in terms of the volumetric flow rate of the dry gas. And this is based on this volumetric flow rate of dry gas, we find that we are giving in terms of the mass of the inhibitor needed per unit volumetric flow rate of the dry gas, that means without the water. Now there are basically two approaches. One is semi-empirical correlation and one are computer simulation, and the basis for the steady state operation is that the incoming mass flow rate of the gas, water and the inhibitor is equal to the outgoing mass flow rates of the corresponding components. Now with this we find that Hammerstedt gives this particular equation to find out the weight percentage of pure inhibitor in the liquid phase liquid water phase, and in this we find this MW represents the molecular weight of the inhibitor, I is the subscript denoting the inhibitor. This is the temperature depression that occurs during the hydrate formation, and this is the Hammerstedt constant. And in this particular table we find for the various these inhibitors EG, DEG and methanol, this kH value and the molecular weight have been listed. And this method has been developed for typical natural gases and for dilute solutions with less than 0.2 mole fraction of the inhibitor, and the glycol injection system generally meet this condition at below minus 23 degrees centigrade, and it generally works for up to 0.4 mole % of EG in between these two temperatures. And for methanol system, with if we consider XW to be the mole fraction of water between, and this is the water mole fraction between 20 and 50 mole % at a temperature of about minus 106 degrees centigrade, we find this is the particular equation is given to find out the depression in the temperature, and in this case the value of the A is given in terms of either the Fahrenheit or in terms of the degree centigrade. Now in this particular equation we find out the minimum amount of pure inhibitor required, and this is what this I100 represents the mass of the pure inhibitor required per unit volumetric flow rate of the gas, and Wg is the mass of water removed per unit volumetric flow rate of gas, and W out and W in are the weight percentage of the inhibitor per unit mass of outlet and inlet stream respectively. In this we consider the outlet stream to be water and the inhibitor only, and inlet also water inhibitor. And with this particular equation we find that this is mass balance, that how much water has been removed by the inhibitor. So, by this mass balance we find we will get this equation, and in this equation if we replace this W out from the Hammerstedt equation we get this particular equation. So, now we find that we can find out the amount of the water removed per unit volumetric flow rate of the gas in terms of the molecular weight of the inhibitor, the temperature depression and the amount of the pure hydrate used and the inlet concentration of the inhibitor. Now, similarly, we can also estimate the methanol, and this is the equation which has been given to estimate the amount of methanol per unit mass flow rate, volumetric flow rate of the gas, and this is the weight percentage of the methanol in water. With this particular equation is used. In this equation we have this function of pressure, temperature, and this is given by this particular equation. In this equation we find that this depends both on pressure and temperature. These A0, A1, A2, A3, A4 and A5, these coefficients are functions of temperature, and this particular table gives us the values of these coefficients as a function of the temperatures. So, this way we are able to estimate the amount of methanol or the amount of the other inhibitors to remove some amount of the water, and these are the references which gives more detail of these methods. Thank you.